I should just stop complaining. Ask and ye shall receive. In discussion today, we were taught exactly what we do with multivariable functions that do actually have limits. It turns out the squeeze theorem applies. Here's how. Also, I only have around an hour in this room. I got here pretty late, so we're gonna have to move pretty quickly if I'm gonna be able to study the statics that I need for the quiz tomorrow. But anyway, let's say that we want to find this limit. If we approach along the y-axis, we find that the function is equal to 0. If we approach along the x-axis, we find that the function is equal to 0. If we approach along the line y equals x, we find that the function is equal to 0. We can use sort of a mini squeeze theorem because we know that this function is always going to be greater than this function because the denominator of this function is smaller than the denominator of this function. We find by approaching along x equals y squared that the limit is equal to 0 as well. We begin to suspect that this thing does have a limit that does exist. So how do we move forward with this? Here's how. We know that the square root of x squared plus y squared is going to be greater than the square root of x squared. We also know that the square root of x squared is just equal to the absolute value of x. Since if you plug in a negative number into the square root of x squared, you are just going to get the absolute value of that negative number. We know that the absolute value of this limit is going to be greater than or equal to 0. It is impossible to take the absolute value of any number and have it be less than 0. We can translate this into this. We simply take the absolute value of the numerator and leave the denominator alone. Since we know that it's a square root, so we are always going to get something positive no matter what. Unless you were using imaginary numbers, which don't exist in the real world, a square root is always going to be positive. Since the square root of x squared plus y squared is greater than or equal to the square root of x squared, which we established is just the absolute value of x, we can basically state that the limit that we're asked to find is going to be always less than this limit right here, the absolute value of y. Because the ratio that the absolute value of x and the square root of x squared plus y squared form is less than 1. So if we multiply that times y, we're going to get something that's less than y. Since this limit is always going to be greater than 0, and this limit right here is equal to 0, we know by squeeze theorem that the limit of this function is going to be 0. Cool. Man, these are going to be some short videos that I shoot. I shot a pretty short one on Friday because I thought I would be able to go back and study more, but I wasn't. I may have some time to study public policy tonight, which will be good for me. But first, statics. In static equilibrium for two-dimensional bodies, we know that the sum of the forces in the x direction, the sum of the forces in the y direction, and the sum of the moments about some point are all going to be equal to 0. There is no net force, ergo no motion, which is, what we're looking for in statics. But actually solving problems is a little bit more tricky than just writing down these sums, of course. Let's do one, shall we? Let's say, for the sake of example, that we have this sort of crane thing here. It is attached to the wall by a pin, and its bottom sort of truss is pushing against the wall with a rocker. Our question is, how are we going to find the forces acting at this rocker, let's call it B, and at this pin, let's call it A? Oh my god, I'm running out of time. Okay, so the first thing we need to do is we need to redraw this thing. We are going to draw it independent of any support, background, anything. We just want the body. It's why we call it a free body diagram. Next, we are going to add the forces that we know are there. My drawing before was a little bit unclear, but there is going to be a force acting at the end here, and a weight force that is acting in the middle here. The force at the end is going to be 23.5 kilonewtons. The force in the middle is going to be equal to 9.81 kilonewtons. Next, we're going to throw some dimensions on this thing. It's going to be important later. Obviously, this is not to scale. Next step is we are going to draw the presumed reaction forces. These reaction forces are going to be how this body remains in static equilibrium. At B, there is going to be a force inward. There is a rocker at B, so remember that a rocker can only sustain a moment of force that is acting perpendicular to it. At point A, there is a pin. Remember, pins can sustain a moment of force in the x and y direction, but not a rotational moment of force. That means there are going to be forces in the x direction, A of x, and forces in the y direction, A of y, opposing whatever is happening in this body. I don't have enough time to do this fully, so bear with me, please. There is something a little bit strange about this problem. We notice that there are no forces acting in the x direction other than the reaction forces, which means that we can't really use the sum of the forces in the x direction are equal to 0. Because we have 3 unknowns here, so we're going to need 3 equations. But two-dimensional rigid bodies are actually kind of flexible in this way. We can keep the sum of the forces in the y direction being equal to 0, and we can also keep that the rotational moment about, say, point A is equal to 0, but instead of writing the sum of the forces in the x direction is equal to 0, we are also going to write the sum of the rotational moments about B are equal to 0. We notice that we have 3 equations and 3 unknowns, B, AX, and AY, which means that we will be able to solve this system of equations. It requires a little bit of creativity and a little bit of flexibility, certainly a hefty amount of practice, which I'm going to need for the midterm that, as it turns out, is next Monday, not tomorrow. Thank God. But this is understandable. It is practically just pattern recognition, knowing which sums you're going to have to use, and then being able to solve systems of equations. Little bit of number juggling, which not too fond of, but hey, what can you do? College, sometimes you gotta do hard things. Oh my god. Oh, I'm about to get kicked out of this room. Okay, Alright, so I can't study this anymore right now. I think I can do a little bit more review before class tomorrow, but that's all I'm gonna have time for tonight. But again, this does seem pretty doable. I think I should be able to replicate it on the quiz tomorrow. So, a bit of a shorter one today, I know, I'm sorry, but nonetheless, thank you all for watching. See you tomorrow.